right, everyone. So, last bit of content related to your analysis of variance. I just left off talking about factorial design. And the reason I want to talk about factorial design is that the way to analyze it is with a factorial ANOVA. So, I'm going to focus on a two-way ANOVA. As I mentioned, you can have as complex a factorial design as you want. It can get out of hand. No matter what level of complexity your factorial design is, ANOVA is going to be the way to analyze it. But I'm just going to show you a two-way ANOVA since that's basically as complicated as we need to get. As I mentioned, I'm not going to make you guys do the hand computations for this one. I have the hand work saved to a different slideshow that I'll show you if you're interested. But the level of time that goes into computing a factorial ANOVA by hand is just excessive. So as long as you can compute by hand a one-way ANOVA, and as long as you can run and interpret a two-way ANOVA in SPSS, that's what we're trying to achieve here today. So let's get started. All right, again, we learned about the one-way ANOVA. This is going to be the analysis that you use when you have a group differences paradigm with a single independent variable with 3 or more levels. So as mentioned, experiments can obviously have multiple IVs, allowing you to interpret and analyze the effects of each IV independently, main effects, that is to say, or the combined effects of combinations of independent variables. So in order to do that, you're going to use a factorial ANOVA. This is going to be the analysis that lets you look at main effects and interactions with your factorial designs. So the example I'll use, let's say we're interested in whether the amount of sleep one gets each night is affected by the amount of exercise and the time of day in which the exercise occurs. So as always, make sure that you're thinking through why this research question applies to the analysis that we're currently learning. Right? You've got your two IVs, amount of exercise, that's going to have the two levels within it, and the time of day, which will separately have the various levels and conditions within it. So those are categorical IVs. The dependent variable, again, needs to be a quantitative variable. Again, make sure that you can keep straight and understand which are the IVs and which is the DV. So think about what all is going into this research question. You have your two IVs, right? And we're going to have our first factor with amount of exercise broken down into your three different levels. Again, recall that a single IV can have as many levels within it as you want. So this is going to be our first factor with its three levels, and then there's going to be our second factor that again has its own levels within it. So in order to run your factorial design, basically what's going to happen is that you're going to need to have participants in all of these groups, all of your cells, and each one of those cells is going to yield a different amount of sleep, which is again our DV. So this is our basic premise. This example, we're theoretically going to be using a between subjects design. Again, this is when each participant is providing you a single score. So this means that all 6 of those cells are going to be completely different groups of people. You can absolutely use a repeated measures design in an ANOVA. It could absolutely be the case that I use a repeated measures design in which participants walk through a series of conditions. This is going to be a slightly different analysis, and how you do it in SPSS is slightly different. That would be what we refer to as a mixed model ANOVA, but in this case, we're keeping everything between subjects. So each participant provides you a single score. Okay, so this factorial design has two IVs, as mentioned. The first factor is going to have 3 levels, and the second is going to have 2. So this is a 3x2 design. So the analysis is going to be what we call a two-way between subjects ANOVA. Again, the ANOVA is a really functional analysis. There's so many different approaches for ANOVA, so that's why it's a more complicated analysis, but there's so many things that you can do with it. Like I said, you can have a complete between subjects design. You can have repeated measures designs. You're able to do both. And you can have as many IVs as you want. So whereas the t-test is limited in its functionality, there's a very limited, very simple design that yields your ability to do a t-test. ANOVA opens up a whole host of approaches. It's a lot more functional in that way. Okay, so this is going to be what we call a complete factorial design in which all levels of one factor are combined with all levels of the other factor. So as I mentioned before, this is basically going to be where we multiply all the numbers in the notation, and that gives us the number of overall cells. And we make sure that we have participants in all 6 of those cells. And in this case, since it's between subjects, it's a completely different group in each of those cells. So again, when I've been saying you need to have the complete combination of all of your IVs, this is what that refers to. This is the term that refers to. So this would, in theory, be what your data looks like before you actually have the numbers in there, right? You've got this visual that depicts your 2 factors and shows you how you can fully break them down. And the idea is going to be that you're going to have participants in each of these 6 cells, and you're going to have a certain number of participants in each of these cells. There's going to be a lot going on here. Okay, so your two-way ANOVA is going to let you examine the influence of both of your IVs separately on the dependent variable, so your main effects. Okay, you can figure out whether or not there's a main effect on exercise on sleep, or you can get a main effect of the time of day of exercise. So just looking at one of the IVs completely collapsing across your second IV. So your two-way ANOVA is going to let you look at these main effects. Okay. Again, when I say you collapse across factors, this is the idea that in order to evaluate, let's say, the main effect of amount of exercise, you completely ignore the fact that some people exercised in the morning and some people exercised in the evening. So you just get the amount of exercise average, and you completely collapse across that time of day factor. The interaction, on the other hand, is going to be when you don't do any of this collapsing. It's when you look at those 6 means for all the 6 cells independently. Again, as I mentioned before, you can figure out that there's an interaction by basically looking to see whether or not one of those 6 bars looks much different from the other. Okay, so as with the one-way ANOVA, the two-way ANOVA is all about partitioning out sources of variance and figuring out the amount of variance that comes from sources that you care about. But now that we have a more complicated design with more IVs, there's a lot more sources that the all over overall variance across all of your participants could be coming from. So you can have some variance between groups and some variance within groups if it's just the one-way ANOVA. The two-way ANOVA, on the other hand, there's more places that variance could be coming from. So variance between groups is going to be what you care about. But when you have variance between groups, the idea is that some of that variance could be due to a main effect of your first IV, some other variance could be coming from the main effect of the second IV, and more variance that's coming from the interaction between the two. So we want to partition out this between groups variance just like we did with the one-way ANOVA, but the idea is it's a little bit more complicated because the variance between groups could be coming from all of these various sources. Now, variance coming from any of those sources would be interesting for the question we're evaluating, but the idea is that we want to quantify the variance coming from these distinct sources. Again, as with the one-way ANOVA, there's going to be some variance within the groups. So there's going to be some variance between scores of all of the people who did light exercise in the morning. But you don't care about that because that's going to be due to just individual differences, measurement error, variance you don't really care about. Variance between the groups is what you care about. But as with one-way ANOVA, you want to quantify the variance coming from these distinct sources. Okay, so again, the logic is the same. It's just that there's more places that variance could be coming from. So the basic approach is the same. It's just that you have to do a lot more math to figure out how much variance is coming from all of these sources. But the basic approach of figuring out the sum of squares within and the sum of squares between, it starts like that in the two-way ANOVA, the same as with the one-way ANOVA. The extra work comes from breaking down the sum of squares between, such that you know how much variance is coming from the main effect of your first IV, the main effect of your second IV, and the amount of variance from your interaction. So this would be, in theory, what your data might look like. So you've got a mean for that first group who had light exercise in the morning. You've got a second mean for the morning moderate exercise, right? So on and so forth. It's a lot of data. So you still would have your ANOVA summary table for your two-way ANOVA. It's just that you need to have lines representing all of these subsequent sources. So you're again going to have information relating to the between groups variance as well as the within groups variance. And you basically have your F statistics that you end up calculating. It's just that you're going to need an F value that indicates the amount of variance that came from factor A. You're going to need an F value reflecting the main effect of factor B, and an F statistic reflecting the strength of the interaction. So a lot more information here. As I mentioned, I'm not going to make you do any of this math because it's a pain in the ass and it takes forever. There's just not enough time to do it. If you're interested, I'm happy to post the math so that you can look into it. But I thought to myself, I don't feel like it. Let's not make them learn how to do that. So basically, what you're going to want to do is just be able to read this information off of SPSS. As with the one-way ANOVA, all of this stuff in the ANOVA summary table that you would calculate by hand is available in your SPSS output. So the structure of the summary table is the same. It's just that there's a lot more information here. So again, obviously, the amount of effort that goes into computing this by hand, it just takes exponentially longer than computing by hand a one-way ANOVA. But this is all the basic information that you care about. Right, you've got a sum of squares and a degrees of freedom for both of your main effects and your interaction that will yield your mean square between for each of those sources, and then you can compute your F statistic reflecting the amount of variance due to the main effects and due to the interaction. As with the one-way ANOVA, you evaluate the F statistic for significance. It's just that in this case, we now have those three Fs to evaluate for significance. So we test for significance for main effects, and we test for significance of interactions. Okay, so as always, we evaluate for significance by evaluating our obtained statistic against a critical F value. You use the same critical F table for two-way ANOVA that you do for one-way. It's just that you need to do that significance evaluation for main effect, and interaction. Okay, so again, you're going to need degrees of freedom and significance level to figure out your critical F value. In the context of this first main effect, you've got your degrees of freedom between and within. That would yield a critical F value of 3.32, and your obtained F for the main effect of factor A exceeds the critical value. What this tells you is that there's a significant main effect of amount of exercise. So basically, even before you take into account time of day, amount of exercise does have a significant effect on sleep. Okay, moving on to evaluate for significance your second main effect, so time of day. Again, you get your critical F value by having your two different degrees of freedom. In this case, the critical F value, 4.17. Again, this clearly exceeds the critical F value. So when your obtained F exceeds your critical F, that's when you reject the null hypothesis. In this case, there's a much stronger main effect of time of day on the amount of sleep. Again, you can go back and you can interpret where this main effect came from by going back and actually looking at those means for time of day, regardless of amount of exercise, to figure out what the main effect was about. Was it the people who got exercise later in the day that got more sleep, or early in the day that got more sleep? The interpretation will involve going back and actually looking at those collapsed means. But the significant main effect tells you that there is a very profound impact of the time of day that you get your exercise on sleep. So then lastly, you evaluate the interaction for significance. Okay? Again, you've got a separate degrees of freedom for your numerator and denominator, and you need both in order to get your critical F value out of the critical F table. But again, we see that our obtained statistic exceeds the critical. What that tells us is that, again, in rejecting the null hypothesis in regards to the interaction, is that there is in fact a significant interaction between amount of exercise and time of day. Those two factors have an interplay whereby there's a unique way that those variables combine to have a unique effect on your DV of sleep. So if you were to map out your actual means and they were to look something like this, again, you can eyeball to figure out where the main effect was coming from and where the interaction was coming from. This is just depicting the means as a line chart, but it would be the same thing if you had a bar chart breaking down your data by amount of exercise and time of day. This is just a line chart instead of a bar chart. But basically, you can look and you can see that it appears that people who exercised in the evening, regardless of amount of exercise, got more sleep. But the interaction, if you were to look and see which one of these data points stands out, that will give you an indication of where the interaction might be coming from. You can see that by far the highest dot is for people who got a lot of sleep in the evening. That's an interaction, right? The relationship between exercise and sleep hinges or is changed by when you got the sleep and how much, when you got the exercise and the amount of exercise you got. So the amount of exercise that you get moderates the relationship of time of day on amount of sleep. There's different ways that you can word what this interaction basically looks like, but we have a main effect of time of day, we have a main effect of amount of exercise, and we have a significant interaction. So that tells us that amount of exercise is important for sleep, time of day when you get the exercise is particularly important for sleep, and that those two variables do in fact interact, such that people who exercise a lot in the evening get the most sleep. Okay, so I'm going to quickly show you how you could do the same analysis in SPSS. Okay, this would be what your data looks like. Again, it's important when you're putting this data into SPSS that you have a variable representing your first factor and a separate variable standing in for your second factor, and that you code the variables appropriately such that the numbers stand in for which level people were in the two factors, and a variable for your DV. Okay, so finding the two-way ANOVA is a little bit tricky. You go to this general linear model drop-down menu and you go to univariate. Okay, what you do is you put your IVs into the fixed factor box. You could have as many in there as you want, and then you put your DV up top in that dependent variable box. You might be wondering why this is the univariate analysis as opposed to multivariate, because this is a factorial ANOVA. Univariate versus multivariate just means the number of DVs currently in the model at one time. So this particular analysis that I've been describing is all about predicting a single dependent variable. So that's why it's univariate. If you were to choose that multivariate option, you could actually throw as many dependent variables simultaneously in the analysis as you want. And the model sort of takes into account that there's multiple DVs and it might be slightly harder to achieve significance on each one individually. If you only have a single DV, just choose this univariate option. It'll only let you put one DV in at a time. Okay, so then you run it, and this is what it shows you. Okay, it shows you the amount of people who are in your various conditions, and then at the bottom of your output is when you see that ANOVA summary table, right? You've got the same information there. You've got your sum of squares for your various sources, degrees of freedom for your various sources, your mean square, and your F statistic. And then over to the right is your significance level. So again, this shows you that there's a significant main effect of exercise, significant main effect of time of day of the exercise, as well as a significant interaction. As always, I'll note that a p-value of 0.000 in SPSS just means that p is less than 0.001. So that's basically how you run your two-way ANOVA in SPSS, and that's how you interpret your output. Okay? Again, this is the most important part of your output, this ANOVA summary table. The basic same things are there as with your one-way ANOVA summary table. It's just that you have variance coming from the additional sources present within your slightly more complex model. Okay, that'll do it for ANOVA. I hope you guys are doing well, and I'll talk to you soon.